Okay, now we are ready to develop the concept of grand canonical assembly by starting developing the partition function of the grand canonical assembly. But in deriving the partition function of grand canonical assembly, we can repeat the procedure we have used for deriving the partition function of canonical assembly by making some adjustment to consider the change of the number of particles inside the grand canonical assembly. Now let us start. We compare the condition of canonical assembly here, and this is grand canonical assembly. We have understood that in canonical assembly, the number of particles is constant, but the energy of the assembly may change, is not a constant. And in case of grand canonical assembly, we have a more general condition where the number of particles is not constant, and the energy of the assembly is also not a constant. So it means that the grand canonical assembly is more general than canonical assembly because the number of particles is constant, but here the number of particles is not constant, but in canonical assembly the number of particles is not is a constant. As we have discussed earlier, that from this assembly we we collect all condition of the assembly in a well-known we know this is the ensemble. This is also ensemble. So the states of the assembly at different times, at different situations, are collected in this, are listed in this ensemble. For example, this is the number of particles is n, but the energy is E1. This is n, this energy is E2, and this energy is E3, and so on. And finally, until this is n, this is the energy is En. Or any states belong to this canonical assembly are listed in the noun ensemble. So the ensemble contains assembly where each assembly is the instant condition of the canonical assembly. So the ensemble is a virtual concept to list all states belong to the assembly. Similarly, any states belong to the grand canonical assembly are listed in the ensemble. For example, this is when the state is N1, E1, this is N2, E2, this is N3, E3, etc. And this is NLEL. All the states belong to this grand canonical assembly are listed in the concept in the non-ensemble. All states belong to the canonical assembly are listed here. So if we know all states, that we know this assembly. If we have listed all states in this ensemble, that we understand the condition of this assembly. Now, in case of a canonical assembly, we have introduced. This is the first state, second state, and third state, and so on. So we have introduced the probability of appearance of states with energy EI, P, EI, is proportional to exponent minus EI of a KT. So we have introduced in the earlier video that because this assembly inside the listed in this assembly have the same number of particles, but they are different in the energy, so the probability of finding assembly with energy E1 is proportional to minus exponent minus E1 over KT. The probability of finding assembly with number n, then energy is EI, is proportional to exponent minus EI over KT. Now, in case of grand canonical assembly, we have two parameters that change. Two parameters that are not constant, the energy and the number of particles. So, in case of this grand canonical assembly, we can use the same concept, but here the probability will depend on EI and Ni. EI is the energy, Ni is the number of particles. Both concepts are introduced because both energy and number of particles are not constant. So this is, we write similarly, the probability of finding assembly with energy EI and number of particles Ni is proportional to exponent minus EI of a KT. This is the same, this is available energy change. And we also introduce another parameter that depend on the number of particles Ni of a KT. So, only depend on EI, we depend on EI and Ni, because EI and Ni are not constant. So, from this concept, because it is proportional, we need to make the relationships is equal. So, to have an equal sign, we multiply with a constant, AI of a KT. Similarly, to have an equal sign, Ni, we introduce another constant, means EI of a KT, exponent minus mu Ni of a KT. So, they're very similar. Because the probability, this is the probability, because in the definition of probability, if we sum or probability for all possible states, this becomes 1. Then, similarly, if we sum all possible Ni, because this is the summation is Ni, EI and Ni, we have to sum doubling the summation of I and the summation of n. For each n, there are a number of I. This is also 1. Similar, very similar. And then, if we continue to calculate the simulation, we then have this one, I C exponent minus EI of a KT equal to 1. Similarly, this one Ni, this one I, B exponent minus EI of a KT, exponent mu Ni of a KT, this is also become 1. Now, because this is constant, we can move outside. I exponent minus EI of a KT equal to 1. This is D. Ni, this is I exponent minus EI of a KT, exponent mu Ni of a KT equals to 1. Now, when discussing the concept of canonical assembly, we have introduced that this one is the partition function. Though there, similarly, in concept of grand canonical assembly, we will define this summation as grand canonical grand partition function. This is known as grand partition function. Is the partition function for the grand canonical assembly. This is the partition function of canonical assembly. This is for grand canonical assembly. So we define here that for canonical assembly, the partition function is E minus EI of a KT. This is for all I. And for grand canonical assembly, we obtain in NI, I exponent minus mu in I of a KT, exponent minus EI of a KT. Now, mu is known as the chemical potential. This is mu is known as chemical potential. Now, from here, we also can write that C equal to 1 of a Z. And from here, we can also obtain that D equal to 1 of a Z grand canonical assembly. This is very similar. So we have this determine here that the concept of a partition function in grand canonical assembly is very similar to the canonical assembly. We only add additional summation of a different n. This is n is the number of a particle inside the grand assembly in the grand canonical assembly, because in the grand canonical assembly the number of particle is not constant. But in case of canonical assembly, because the number of particle constant, we have only one summation, of a different energy of the assembly. Now we have to make a summation of a different energy and different number of particles. So in case of canonical assembly, we only do one summation of a different energy, because the number of particles is constant. But in case of a grand canonical assembly, because energy and number of particles are not constant, we have make a summation, double summation, one summation of a different energy and one summation of a different number of particles. So look at here, this is very different. So if in this case the number of particles is constant, to means that only one n here, so we can remove the summation, because we only have one n. No, in case of general grand canonical assembly, we have a different n, different number of particles. But if we only one n, the number of particles constant, so we will only have this summation. That means that the results will be the same as this one. This is the canonical assembly. So that means we prove here that in case of number of particles is constant, the partition function of the grand canonical assembly becomes similar to the partition function of the canonical assembly. Now, the question is this definition correct? Is this definition correct? To mean that, can we obtain the macroscopic properties of the assembly from this partition function by simple procedure? In case of canonical assembly, from this definition, we can derive simply the properties, the thermodynamics properties of the assembly. For example, the energy is like kt squared, the dou of a natural logarithm of this one. For example, in case of a canonical assembly, we have energy is kt squared dou of a dou t ln z canonical assembly partition function. The same question can be applied to the concept of a grand canonical partition function. Can we obtain the same parameter, the same macroscopic properties from this function as simple as this one? This is the challenge, and we will discuss in the next video, that from this definition, we actually able to derive the macroscopic, the thermodynamics properties of the very general assembly, the grand canonical assembly. And we will discuss in the next video how to derive that macroscopic property, so that we can compare the experimental result in macroscopic condition with the microscopic behavior of the atom or molecule inside the grand canonical assembly. We will consider in the next video.